It covers a broad physics program, dedicated physics program on two items, hadron spectroscopy and nucleon structure, which of course are at the basis of the acronym. We use muon and hadron beams, proton and pions, and we have a spectrometer which is good both for studying the structure of the nucleon and the spectroscopy of hadrons. Now, this is an artistic view of the spectrometer. By now, it is in operation, as I said, since 10 years, but when we constructed it, really it was state of the art. We used novel techniques like gem tracker, like micromegas tracker, photon detectors using multi-wire proportional chambers with photocathodes, namely cathodes with a cesium iodide foil, and so on and so forth. And in particular, we were the guinea pigs of the IT division of CERN for what concerned computing. We were the first to use these distributed farms of PC and to digest the data in petabyte quantities. And one of the detectors which was extremely useful in all our programs is a rich detector. This is an example of the performance, the separator. We can separate pions, kaons, and proton up to 750 GeV. This is a fairly large structure, and I mention it not only because it is a rather sophisticated instrument, but because, for instance, these mirror walls, which you see covers some 30 square meters, the mirrors were all fabricated in Czech Republic, and this is the mirror wall, and this is the technique I mentioned, which uses multi-wire proportional chambers with photocathodes, a fairly cheap technique to cover large surfaces, which turned out to be quite good. We had covered the 6 square meters of photosensitive region, and these detectors, of course, we suffered somewhat in the central region. So in 2005 we had a first upgrade, and we changed the detectors closer to the beam with multi-anode photomultipliers. And again, to save money, we are not very rich people, we used a lens system which actually was studied, developed, and tested in collaboration with our Czech colleagues. So we have presently a sort of hybrid system in which here you see this is the lower half of the photon detectors, and these are this is the back, the readout planes of the multi-wire proportional chambers, but the central part has been replaced by these multi-anode photomultipliers, which are, as I said, coupled with a nice lens system in which we involved our Czech colleagues who, as everybody knows, have a reputation in optic and quartz. So another item, this is an example of the performance. You see this was prepared for the Olympics. And you see there is a remarkable difference of behavior presently from the central part, which has an average 60 photon detected along a ring, and the outer part where the average number is 10. So we have considerably improved the system. And of course, now we are thinking of a second upgrade. Of course, we want to improve again also on these detectors, and this is the next step we will do, changing this multi-wire proportional chamber with new thick gem techniques. And again, this will be done in collaboration with Prague. And another important instrument in the experiment is the polarized target. Of course, this is a very sophisticated system. This is the cryostat and the target holder, and the magnet, a special superconducting magnet with a highly homogeneous field. The target is divided in 3 pieces, which can be oriented in opposite directions in order to take data with the 2 polarization states at the same time to minimize systematics. But okay, and also in this system, Prague people are giving a hand. Okay, as I said, we started taking data in 2002, and this is a list, a detailed list of what we've done. I don't think you are very much interested in the list, but well, basically most of the time we spent with the muon beam, 160 GeV typically, but also 200 GeV, and polarized target to study structure. And we had 2 years dedicated, 2008, 2009, with hadron spectroscopy, in which case we had hadron beam and liquid hydrogen target. And needless to say, in these 2 years we have collected a huge amount of data. And for the time being, we are satisfied. Of course, cross-sections are large. And now, this is an old transparency I showed in 2000 in Osaka, the spin symposium, which I think is still true. I mean, I was really pleased when CAMPUS was approved. It was approved in '97, and I think that most of you remember how hard times we had at CERN in '97, '96 and '97. So it was really a good achievement, and I regarded that as an acknowledgement that it is still worthwhile to invest in trying to answer some questions which have been with us since 30 years. That was 10 years ago, so now it's 40 years. Very simple questions, like how is a nucleon made up, in particular the spin structure, and are there known QQQ or QQ bar hadrons, so the eternal issue of exactics, and these are fundamental problems of fusivity. In particular, when the experiment started, there was a huge debate about the role of the axial anomaly to the spin of the proton, and as several decades, there is still the issue of the glue balls, the existence of the glue balls, which is deeply embedded in the non-abelian nature of QCD. So, I'll try to be very fast and just giving the essence of what we are doing. First, with the hadron program. I think, since this is, in a way, old physics, I think everybody knows that we don't know whether these exotic states, hybrids, glue balls, multi-quarks, really are there or not. There are hints coming from many experiments and several laboratories, but it is not really clear whether they are there or not. And we are trying to do our job in clarifying the situation. There are many channels: central production, diffractive dissociation, gluon-rich final states. I just picked up a couple of transparencies on the work we are doing on diffractive scattering. A nice channel starting from a pi minus beam is a charged 3 pi state. And we have, these are just data from 2008, and this is not even the full sample of 2008. And we had 2 here. And this is 100 million. It's 100 million. In a single bin, which has 5 MeV, we have typically 1 million events. So the statistics is unbelievable. Unbelievable. It's by far superior to any other experiments. And of course, you need a model, you need a tough partial wave analysis, you need to reconstruct the spin density matrix. This is just a flash of the major waves, the accuracy with which we can reconstruct the major waves, the rho pi, the f2 pi, the rho pi d wave. You see that they are really extremely well determined. Of course, this is not the full story, but we have 3 independent programs to do partial wave analysis. And In the analysis, we reconstruct presently up to more than 50 waves. 50 waves. Of course, to fully exploit the potential of campus, it is necessary to have excellent knowledge of the apparatus. And this is Monte Carlo, so it's a lot of work. It's a lot of work, but we are doing. Another issue we have addressed in the Hadron program is an interesting test of chiral perturbation theory, which is just a low energy limit of QCD. And what we are measuring is the polarizability of the pion and of the kaon via Primakov scattering. Essentially, we have a pion beam. We select Primakov scattering, namely Q square as close to 0 as possible, and then we look for the scattered pion and a gamma, a high energy gamma. This is Primakov scattering. So in this way, we measure, from the departure of the point-like cross-section, we extract the polarizability. And this is something which our theoretical colleagues working in chiral perturbation theory can predict. An experimental situation is confused. This is what exists, so you can fill up a plane. This is our preliminary result from a test run we had a couple of weeks in 2009. You see, this is the prediction. This is the prediction of chiral perturbation theory. We are, say, well, of course, compatible with this prediction. But this is preliminary. This year, we have taken almost the full year of data in this Primakov scattering, and we should really provide a very precise measurement. Okay, so much for the Hadron program. Now I jump to the spin structure of the nucleon. Now, of course, the spin structure of the nucleon is on the table, is a matter of discussion since the result of the EMC collaboration almost 25 years ago. This is the measurement of the EMC collaboration, the measurement of G1, the spin-dependent structure function of the proton as a function of x. And this is the integral of G1 from x equal, from a certain x value to 1. So if you extrapolate to 0, essentially you get the first moment, and this was the result from which you extract the quark contribution to the nucleon spin. And this was the most famous spin prizes, the spin problem, namely that the spin of the nucleon was not accounted for by the spin of the quark. And this was and still is a problem. This is a problem, and well, we know why. Because, the fact that the nucleons are not point-like particles and have an internal structure, this is obviously well known. It's known since 1930s, because when the magnetic moment of the nucleons were measured, and the magnetic moments of the nucleons are, for the proton, 3 times the nucleon Bohr magneton, and 2 times the neutron. And these numbers could not be understood, but they were a clear message that they are not Dirac particles. Okay, the problem is that the quark contribution of the nucleon spin came out in an extremely elegant way in the constituent quark model. In particular, the magnetic moment were calculated with elementary algebra. You just take a wave function, an SU6 symmetric wave function, namely you take the quark, the constituent quarks in an S state, and you get immediately the right values for the proton and for the neutron magnetic moment, and of course for the ratios. And this cannot be an accident. And in this model, the spin of the nucleon is just given by the spin of the quarks. And this thing was well rooted in our minds, in the minds of everybody. So this was absolutely at variance with the result of the EMC collaboration, because the same quantity which was measured, namely delta sigma, which is the sum of delta U, delta D, delta S, namely the contribution of the quarks to the nucleon spin, which in the EMC measurement was small and even compatible with 0, in this model had to be 1. And 1 and 0 are fairly different. So this was the beginning of the story. You had a huge amount of papers on this, a critical review of the concepts. Of course, you have C quark, you have gluons, you have orbital angular momentum, so the spin sum rule indeed has many bits and pieces. And there was immediately some homework to be done, namely, first of all, to remeasure the proton, then to measure the neutron, and then there was the big message to measure the contribution of the gluon, because in the constituent quark model, you don't have the gluons, and you hope to make up the spin just with the quarks. Let's see what the contribution of the gluons is. And there was a way of thinking that the gluons might be very important. So there were many experiments and a worldwide effort since a couple of decades. You see, this business of polarized deep inelastic scattering started out at SLAC with E80 and E130. Then we had the EMC experiment at CERN, and here in '87 we had a problem. And then you had immediately the SMC experiment being proposed and running and approved experiment at CERN, other experiments at SLAC, Hermes experiment at DAISY. You had the collider, the polarized proton-proton collider at RIC being approved, again to check transverse spin, but also delta G, the contribution of the gluon. You have JLab. So it's really an international effort. And at CERN, from SMC, essentially, we passed over to COMPASS with an improved program. And I'm saying that a lot of work has been done. So back to this spin sum rule. These quantities which I have indicated as delta U, delta D, delta S, the contribution of the individual quarks to the spin of the nucleon, actually are integrals of the helicity parton distribution function, where the helicity is essentially the difference between the PDF in one spin state, say with where the spin of the parton is antiparallel or parallel to the nucleon spin, in the longitudinal mode, namely with the target spin, the nucleon spin, oriented as the incoming lepton. Now, these quantities can be extracted from the deep inelastic scattering cross-section asymmetry for parallel and antiparallel lepton and nucleon spins. So, and this in inclusive deep inelastic scattering. The way, the expression is this one. This is just very similar to the expression for the cross-section in the unpolarized case, in which you have two different structure functions, the F1 and the F2. So G1 is obtained just from the cross-section difference of the deep inelastic scattering in pure spin states. And as I said, there are several experiments which have measured this quantity. And this quantity in the parton model, G1, is essentially the weighted, the charge-weighted helicity functions of the quark and the anti-quark. Okay. This is an example of the measurements we are still doing at COMPASS. This is the run on the proton we had in 2007. This is the run of the deuteron we had in 2002, 2003, and 2004. You can see that in the very low X region, essentially we are the main players of the game. And the very low X region is very important for getting the first integral, because you have to extrapolate to zero value of X. And we are the main players. The only other experiment is the SMC experiment, but you see that SMC could not compete with compass. Okay, another very useful thing is these are the measurements we've done in 2011, which means last year. We have remeasured the proton, so we have 2 years of measurement with the proton, and a very useful exercise is to get the difference of the first moments of the proton and the neutron. This is the difference of G1P and G1N, which is the singlet part of the structure function, and this is the integral, which of course allows to check the most famous Bjorken sum rule, which as far as we are concerned is perfectly respected. Okay, so that regard the quark. So clearly the quarks, the contribution of the quarks can be measured from G1, but that is not the full story. Actually, COMPASS was designed mainly to measure delta G over G, and we are unique in this work. There are 2 ways, basically from the cross-section asymmetry for charm production or for high PT hadron pairs. The indirect method are from scale violation of G1, because G1 actually is a function of X and Q square. You do QCD fit using delta Rayleigh Parisi formulas, but since we are all fixed target and relatively low energy, this second way has no sensitivity. And while the direct method is fine. And these are the kind of diagram which is useful for measure the gluon polarization in a polarized nucleon. Of course, the nice way is if this QQ bar pair is a heavy quark, like CC bar. And we are looking, because there is basically no charm, intrinsic charm in the nucleon. So if you find charm in the final state, that is most likely produced through the fusion of the photon and the gluon. So this is what we have exploited. And to make a long story short, because we have spent years and years, this is a collection of all our measurements, and you see from the scale that there is not a large contribution from the gluon to the nucleon spin. So the spins puzzle today can be summarized as follows. Delta sigma has been measured rather well by us, by Hermes, by Slack experiment, and it is 1/3, it's 0.3, at a level of 10% accuracy. So it is not 0, but it is not 1. Definitely it's not 1. Delta G is small. I haven't written a number. By the way, at RIC with the polarized proton collider, they are also addressing delta G, and they come to the same conclusion. So, looking at this expression, obviously you need to address orbital angular momentum. And that is a tough business. That is a tough business, and that leads to a better knowledge of the nucleon, which you can achieve through these GPDs, the generalized parton distribution, and in particular there is Xiandong Ji has written a sum rule from which you can really extract the total angular momentum of the partons inside the nucleon. But the fact that there is orbital angular momentum has stimulated a growing interest in transverse spin phenomena, because if you have orbital angular momentum, clearly you must have transverse momentum, and transverse momentum couples with transverse spin. So that is the new frontier to describe the structure of the nucleon. First of all, it was rediscovered that at leading order you need 3 parton distributions. So not only the unpolarized parton distribution and the helicity parton distribution, but you have the transversity parton distribution, which has a similar distribution as the helicity, but it relies a transversely polarized quark in a transversely polarized nucleon. These quantities can, while the first 2 can be measured in inclusive deep inelastic scattering, this one cannot, and is still poorly known. But it can be measured. Originally, it was introduced almost 30 years ago by Ralston and Soper, and it was suggested that it could be measured in Drellian processes. But Drellian processes with polarized target have never been done. We hope to do it in COMPASS in the near future. That has already been approved. But there is an alternative way suggested 20 years ago by Collins, which relies on a possible correlation between spin of the quark and transverse momentum of hadrons. This correlation induces a measurable azimuthal modulation of the hadrons. So if you have a transversely polarized nucleon and you produce a transversely polarized quark, this transversely polarized quark can have a left-right asymmetry in the hadronization. And this can be used as a quark polarimeter. And this was a conjecture, of course, but it is correct. It works. It works. We have measured this. These are our measurements. These are proton data on COMPASS 2007. So this asymmetry is definitely different from 0 and allows you to measure the polarization, the transverse polarization of the quark, and get to the transversity. This is this new PDF as extracted from our theoretical friends. There is an alternative way to access transversity. Also, if you produce 2 hadrons define a plane. And again, if you have a transversely polarized quark hadronizing into 2 hadrons, there is an asymmetry, an azimuthal asymmetry in the plane of the 2 hadrons. And again, this is there. These are our measurements. So this is there. And this is for pi, this is for k pi. And again, we can extract the transversity from this data. These are the transversity of the U quark and of the D quark as compared with the transversity extracted from the Collins asymmetry, which I have shown a couple of minutes ago. But this is not the full story. This is not the full story, I'm sorry, because Collins' effect relies on transverse momentum. And if you accept the idea that you have a transverse momentum in your partons, then you open up a Pandora box. If you, okay, I skip the text, but you have more correlation possible. If you go beyond collinear QCD, you can have what is known as the Sieverts function. Namely, you can have a correlation between the intrinsic momentum of the quark and the spin direction of a transversely polarized nucleon. And this again leads to an azimuthal single spin asymmetry. Same thing is true for the so-called Boole-Mulder function. Again, there can be a correlation between the transverse spin of a quark and the transverse momentum of a quark in an unpolarized nucleon. And the properties of these functions, Sieverts and Boole-Mulders, are extremely interesting. They are T-odd, and they have been studied. They were believed for some time to be 0, because of T invariance, but this is not the case. It was shown that, first of all, they are necessary for gauge invariance of the theory, and then it was shown that they are due to initial and final state interaction, and in modern QCD, this relationship has been demonstrated, namely that these distributions, Sievers and Burmulders, change sign whether they are measured in series or in Drell-Yan processes. And this is a test, fundamental test of, a very important test of QCD, which again we will do with the Compass, within Compass, as soon as the machine restarts a couple of years from now. This is a cartoon in which one explains the reason of the sign change. So this is the full picture. So it is not true. It is not true that we have two Parton distribution functions to describe the nucleon. Actually, we need 6 PDF, which are called TMD, transverse momentum dependent PDF. So life, as usual, has become a little bit more complicated, but this Sievers function, in which I just mentioned, we have measured, and in series, and you see, it is definitely, at least for positive hadrons, it is definitely different from 0. So the effect is there. Clear positive signal for H+. And this is independent evidence for orbital angular momentum of quarks. Independent evidence from what is mentioned about the longitudinal case. And here I compare our data with Hermes, just taking the data at large X, because this is the X interval covered by Hermes. And Hermes had measured basically the same thing, but you see the signal is stronger. And this is important evidence of the Q-square evolution of this TMD. This is the first measurement of the Q-square evolution, which is not the standard Altarelli-Parisi Q-square evolution, but it is stronger. Okay. So these are very new developments. So the conclusions, this is the last. The quarks contribute 1/3 to the Newton spin, full stop. The relative size of the delta G and orbital angular momentum are not clearly assessed. And in the homework of Compass 2, we will try to address at least partially this issue of the orbital angular momentum measuring DVCS, namely deeply virtual Compton scattering processes. Second conclusion is that transverse spin and momentum phenomena, new properties of matter have been unveiled. This transversity, Collins effect, Sievers effect, and these are new things, brand new things, which some were not even existing when we started experiment. Sievers asymmetry was not even mentioned in our proposal. It was, somebody demonstrated that it had to be 0. And other correlations are still possible, like the Burmulders correlation. So, Compass 2 should be able to test the predicted sign change of the Sievers function from series to Drell-Yan, as I said. This we had in our shopping list. And we should be able to perform precise measurements of unpolarized series azimuthal asymmetries. And this is a way to access the Burmulder asymmetry. And let me remind that Compass has a great discovery potential. I have not come here with exotics, the proof of the existence of exotics, but we have a great discovery potential for blue balls and hybrids. Thank you.
Thank you very much. We are slightly behind the schedule, but still we have time for some questions, please.
Yeah, keep it with hundreds of billions of events.
The question is, how do you turn this discovery potential into a discovery for glueballs? I mean, what it is at this point that will finally lead you to pull out a glueball?
Well, I have not entered into detail, but we have capability of detecting neutral states at the same time, in particular eta. So we detect from gamma-gamma, we reconstruct eta, so we looked for eta-eta states. And these states are believed to have, well, glueballs should decay preferably in eta. This somebody told me. I don't know whether it is 100% true. You tell me. But that is the basic message. That is, we are capable of investigating, well, first of all, low mass states. We are talking about 2 GeV typically. This is where we have the highest sensitivity. And we have a huge amount of data, and we can explore different production mechanisms and different decay channels. Different production mechanisms because we can have proton beam, we can have pion beam, positive and negative, and kaon beam. So we can, in the same spectrometer, have different probes and several decay channels, charged and neutral.
Okay, another question?
With high statistics.
Yes?
You have shown a very nice result about the polarizability of pion. Are you able to do the same measurement for kaons?
Yes, yes. We have about 4% of kaons in the beam, 3 to 4%, and we take the data at the same time. We have 2 CDARs, special Cherenkov counters, with which we tag the incoming particle. And at the analysis level, we measure the 2. We have nothing in the data I have shown because that was the result of a couple of weeks of test beam. But this year we have taken data from the beginning of the run in May until late September. So we should come up with some results on the kaon.
Okay, let us thank the speaker again.